Welcome back, everyone. Today we're starting chapter 13, which is our chapter on game theory. And I think this is a really cool chapter because whereas what we've been doing in recent chapters is adding context and texture to things you already know from principles of micro, what we're doing in game theory is introducing a novel concept. And that concept is one of strategic behavior, meaning the choices you make are going to take into account the actions, the decisions, the responses of other people. So the plan for today is to really just introduce some of these core concepts in game theory, and then in the next lecture we're going to build that out with more examples and more applications. So let's start with just some introductory vocab. A game is a situation where players or participants, they can be people, they can be firms, they can be countries, make strategic decisions that take into account each other's actions and responses. The payoff is the value associated with those outcomes. And here we can think of payoff as utility if it's a person, profit if it's a firm, some sort of impact or change to GDP if it's a country. Given that we have players and payoffs, and this strategic game, we now want to develop a strategy, which is just a plan or action for how we're going to move forward in this game. And since this is econ, we're concerned with the optimal strategy, the strategy that maximizes your expected payoff. And keep in mind, we're talking about expectation here because we don't know with certainty what the other player is going to do. What this means is we're going to have to make choices based on some sort of beliefs. And the belief that we will be operating from is that the other player is rational. And in this sense of the word, it means the other player is acting to maximize their own payoffs. In the back of your mind, you should be pushing back on this somewhat, because every game we're going to see in this chapter has complete information on what those payoffs are. But what we're going to see in the next chapter, chapter 17, is we might not always have all that information. Conditional on that, though, we're going to assume that players are rational, that they're acting to maximize their own payoffs, and with that information in mind, we are going to make our choices, formulate our behavior accordingly. This can be hard, even though we have perhaps symmetric games and perfect information. Not only can we describe games by their rules, their players, their payoffs, but we can describe games by how the players interact with one another. And broadly speaking, we can think of two classes, cooperative and non-cooperative. Cooperative is one where players can benefit one another, which will allow them to negotiate contract. They can plan strategies together. Non-cooperative is one where players are not working together, and thus contract enforcement is not possible. So think to some of your own experiences in the market to help understand what a cooperative game looks like. We know from our discussion of surplus that everyone wins from participating in a market. Buyers win by getting something they want. Sellers win by hopefully making a profit. So market participation between a buyer and a seller is an example of a cooperative game. If you buy a rug, you gain a rug, the seller gains $100. This is a cooperative solution. But what if we're comparing the behavior of two sellers, where there's only one of you to buy that rug? You shopping at the first store necessarily means you're not shopping at that second store. This is non-cooperative. And in making the seller of one rug better off, the other seller is worse off. It might be useful to think about how games are depicted. And this can be a little difficult to grasp at first, but once you familiarize yourself with the process, it actually becomes quite straightforward. And games are typically depicted as playoff tables or matrices. These matrices allow us to show three things. One, the players in the game, typically described as row and column players. So we've got row here and column here. Two is the strategies, or the choices that these players can make. And three is the payoffs from those choices. So how do we read a game? Well, each player, that being row and column, can make one of two choices. We'll call them choice A and choice B. In this case, the choices are symmetric. Both row and column have choice A and choice B available to them, but there's no need it has to be. We could have just as easily said that the column player, for instance, can play choice E and choice F. But for simplicity's sake, we'll say both players, row and column, can make choices A and choices B to them. The key thing here is that your payoff, let's say you're the row player, your payoff depends not only on your choice, but also the choice of the column player. And so in each cell of this matrix, we have payoffs listed. The convention is that the row player is listed first, the column player is listed second. And in each cell of this payoff matrix, we have the payoff to both players for the corresponding choices. So in the event that both players choose choice A, we list in the payoff matrix their payoff for row and the payoff for column, conditional on both players choosing choice A, and so on and so forth for B and B and A. So here in this cell, we have A comma B because by convention, we list the row player first. So the row player is making choice A, column player is making choice B. That puts us in this cell right here with the red circle with a corresponding payoff for the row player at payoff row A comma B, corresponding payoff for the column player at payoff comma A comma B. Again, it's kind of difficult to understand these until you get familiar with the setup. So rather than speak in these abstract terms, let's put some numbers on it. In this game, we have two players. We've got Dean Garrett and we've got President Wu. And again, this is a game, we're talking about strategic decisions. Their payoffs depend on the behavior of one another. So let's describe this game. Dean Garrett and President Wu are looking for a place to hang out after work. Dean Garrett really likes hanging out at the boathouse. President Wu really likes hanging out at Vixen's Den. But more importantly than that, they want to hang out with one another. Now, we all know how bad Sweetbriar Wi-Fi can be, so they're not getting each other's snaps. They haven't been able to plan this in advance. They want to meet each other up after work, but have no way of communicating. Let's see how this game might play out. And all we're doing right now is describing the potential payoffs as a response to those choices. We'll learn more about how they can make those choices later in the chapter. But we'll go around the payoff matrix clockwise and describe the payoffs and choices associated with it. So, in the first choice, they both choose the boathouse. Remember, Dean Garrett likes the boathouse. If they both meet up at the boathouse, Dean Garrett gets a payoff of 2. President Wu likes hanging out with Dean Garrett but doesn't like the boathouse as much. President Wu gets a payoff of 1. What about their other possible choices? What if Dean Garrett goes to the boathouse and President Wu goes to Vixen's Den? Here, neither gets any payoff. They both get a payoff of 0 because they didn't successfully meet up after work. Similarly, If Dean Garrett goes to Vixen's Den and President Wu goes to the boathouse, they both get a payoff of 0. They didn't successfully meet up after work. 0 to Dean Garrett and 0 to President Wu. And finally, if they both go to Vixen's Den, Dean Garrett gets a payoff of 1, but President Wu, who really likes Vixen's Den, gets a payoff of 2. Go over this slide a minute or so more on your own to make sure you're comfortable with it. But now that we know how these games look, how payoff matrices work, we can talk about perhaps how people might make choices in a game. And remember, our word for making those choices is strategy. The first thing we want to look for is a dominant strategy, which is a strategy that earns you more, that is optimal no matter what your opponent does. So let's first go over this playoff matrix for these two firms, Firm A and Firm B, that are deciding whether or not they want to advertise. If they both advertise, Firm A gets 10, Firm B gets 5. If Firm A advertises and Firm B doesn't, Firm A gets a lot of payoff. It gets 15. Everyone says, oh, we should go buy Firm A's product, and Firm B doesn't get anything. If Firm A doesn't advertise and Firm B does, Firm B gets a little bit more payoff than Firm A. Firm A gets 6 and Firm B gets 8. And if neither advertises, Firm A gets 10, but they're not recouping too much of Firm B's market. Firm B still gets some payoff at 2. So what does it mean for a strategy to be dominant? It means that the player in this game can make their choice regardless of the other player. So let's look at Firm A's choices. And we don't have to consider Firm B at all right now. We just know that in one instance, if Firm A advertises, they get 4 more than not advertising. And in the other instance, if Firm A advertises, they get 5 more than not advertising. So before we even get to what Firm B is going to do, we know that Firm A is going to advertise, because no matter what Firm B does, Firm A is better off. In other words, advertising is a dominant strategy for Firm A, I apologize. Now let's look at Firm B's choices, which means we're going to draw blue X's through Firm A. So in one situation, Firm A makes a choice, and it's better for Firm B to advertise. They get 5 more than they would in the other situation. In another situation, Firm A makes a choice, and it's still better for Firm B to advertise. Note we're comparing this 5 to this 0, and we're comparing this 8 to this 2, because we're looking at Firm B's payoff. So it looks like Firm B has a dominant strategy of advertising. Advertising is a dominant strategy for Firm A. Same is true for Firm B. No matter what Firm A does, Firm B does better by advertising. No matter what Firm B does, Firm A does better by advertising. The outcome is therefore that both firms advertise, and we wind in this payoff cell where Firm A gets 10 and Firm B gets 5. Note, we call this outcome an equilibrium because no firm has any reason to deviate from that. Suppose we are at this dominant equilibrium, this 10-5 equilibrium, and for whatever reason, Firm A said, you know what? I changed my mind. I really don't want to advertise. If that happened, they would be sacrificing payoff. If we were at this equilibrium and Firm A said, I don't want to advertise, they go from a payoff of 10 to a payoff of 6. And given that we have that presumption of rationality, that everyone is doing what's best for themselves, firm A would never make that choice. Similarly, suppose we're at this dominant equilibrium and firm B says, you know what, I don't want to advertise. Then again, they're sacrificing payoff. They would go from 5 to 0, so they would never make that choice. In dominant strategies, we're at an equilibrium when each firm is doing the best it can regardless of what its competitor is doing. We like dominant strategies because they make analyzing a game really easy. But in such a world, we're not really looking at strategic behavior because your choice doesn't depend on what the other person is doing. And not every game has a dominant strategy. So let's look at that advertising game again, but I've changed the payoffs around a little bit. Let's still look at firm A. So I'm going to X out firm B's choices. If firm B chooses to advertise, firm A also wants to advertise. 10 is more than 6. But if firm B chooses to not advertise, firm A does not want to advertise. 20 is more than 10. In other words, firm A does not have a dominant strategy, and its optimal decision depends on what firm B does. This means two things. One, firm A now needs to engage in some form of strategy, some strategic behavior. And two, we as economists need to develop an equilibrium model based on not just dominant strategies, but responsive playing. That equilibrium model that we've come up with is called a Nash equilibrium, after John Nash, who won the Nobel Prize in 1994. So whereas a dominant strategy is you doing the best you can no matter what the other player does, without regard to the other player, a Nash equilibrium is you doing the best you can given what the other player is doing, and vice versa. You doing the best you can given what the other player is doing, the other player doing the best they can given what you are doing. In other words, a Nash equilibrium is a mutual best response. Let's explore this concept in a new payoff table, the product choice problem, where both firm 1 and firm 2 are making cereal. The cereal can be crispy or it can be sweet, and their payoffs depend not only on what they're doing, but what the rest of the market has done as well. So again, to get us comfortable with these payoff tables, let's go through it. Suppose both firms make a crispy cereal. That puts us in this cell. And both firms lose 5 here because the market is flooded with crispy cereals. Crispy cereals are a little healthier and no one likes that. What if firm 1 makes a crispy cereal and firm 2 makes a sweet cereal? That puts us in this cell here with the green X. Then both firms are making $10. The market's diversified. Healthy people are getting healthy cereals and sweet people are getting sweet cereals. Seems pretty good. Moving down to the bottom left corner, which I'll mark with a red X, firm 1 is producing a sweet cereal, firm 2 is producing a crispy cereal, and we see the same thing. Both firms get a payoff of 10. Healthy people are getting their healthy cereal, the market is diversified, sweet tooth people are getting their sweet cereal. And then we'll finish off the table with this purple X. Again, firm 1 and firm 2 are making the same choice. The market is flooded, and in this case, since it's both sweet cereals, we all have diabetes and everyone loses 5. So, can we come up with a mutual best response here? Can we come up with a Nash equilibrium? Well, let's assume we're both in the crispy world. If we're both in the crispy world, and someone comes to you and says, listen, you're making a crispy cereal, but I'm going to give you the chance to change your outcome. Would you do that? So if we're both in the crispy world, and firm 1, for instance, decides they'd like to start producing sweet cereal, they are better off. They have incentive to deviate from that strategy. In other words, crispy is not a best response for firm 1 if firm 2 is also producing crispy. Same thing on if we flip the firms, if both firms are producing crispy cereals, firm 2 has incentive to deviate. They also want to start making sweet cereals. 10 being more than -5. Let's look at another outcome. Let's look at the outcome where firm 1 is making a sweet cereal and firm 2 is making a crispy cereal. That puts us in this bottom left corner where the payoff is 10 to each. If you're firm 1 and you're making a sweet cereal, do you want to then switch to a crispy cereal? No, because that just reduces your payoff by 15. You'd go from earning $10 in the market to owing $5 in the market. That's a bad change. Same thing, I'll put a big X to denote that. Same thing for firm 2. Firm 2 is making $10. They have no incentive to switch and start making a sweet cereal where they'd be owing $5. In other words, neither firm has an incentive to deviate. The strategy sweet crispy is a mutual best response and a Nash equilibrium. NEQ, Nash equilibrium. We'll also see that the outcome crispy sweet is the same thing. No one has incentive to deviate. This is a mutual best response and a Nash equilibrium. This isn't the only way for us to look at strategic behavior, and indeed we see strategy in all types of situations in the market. So let's consider a new game. Here I'm not going to write a payoff matrix, but we're going to see a little diagram where you are selling paletas on a beach. All paletas taste just as good. It's a hot day. Everyone enjoys a cool treat. But what they want is to just go to the closest paleta person. No one wants to walk across hot sand to get their sweet treat. Those red X's indicate hot sand. So if the beach is 200 yards long, where do you locate your paleta stand? Keep in mind that everyone just goes to the closest paleta stand. So let's say you decide, for whatever reason, to locate your stand here, and your competitor decides to locate their stand here with the C. Which customers do you get? Well, you get everyone on this side of you, and you get everyone on the halfway point between you and the competitor. So you get customers from this end point of the beach to here. What about your competitor? Where are their customers coming from? And I'll draw their customers in green because they're making a lot of money. Well, certainly everyone over here is going to their stand. They're not going to walk past stand C to get to you. And everyone on this side of the halfway point between their stand and your stand is also going to them. Remember, your customers just want to go to the closest stand possible. What does this mean in terms of Nash equilibrium? Both you and your competitor will locate at the exact midpoint of the beach, where you'll get everyone from this side and they'll get everyone from this side, with the assumption that customers are spread evenly across the beach. We actually see this a lot in real life, in the naturally occurring world, where gas stations are located across the street from one another. We tend to see banks located across the street from one another because people don't really care about whether they get their gas from Chevron or Shell. They just don't want to have to drive a long way for it. Let's stay at this point and confirm where your customers are coming from here and their customers are coming from here. What happens if, for whatever reason, you decide to move your paleta stand down here? I'll mark it with a big Y. All of a sudden, you're going to lose about this many customers. In other words, you have no incentive to deviate from your midpoint on the beach. The same thing with your competitor. They have no incentive to deviate. You're both doing the best you can given what the other person is doing. This is a Nash equilibrium, a mutual best response. Let's suppose, one more time, that you locate your stand right here, just for fun. Take a minute to consider where the other person is going to locate their stand. And I'll put this in dark purple. They'll locate exactly next to you. So now everyone on this side of the beach from their stand down is their customer. If you happen to locate here, their best response is to locate exactly next to you. You, however, now have incentive to deviate. This is not a mutual best response because you have incentive to move your paleta stand, and you have incentive to move it right here next to them. And so on and so forth until we wind up where we were at our Nash equilibrium, at our mutual best response, where everyone is at the midpoint of the beach. So let's practice what we know about game theory for a little bit. Press pause on this video and see if you can go ahead and find the Nash equilibrium in this game. So you should have come up with invest as a Nash equilibrium, a mutual best response. Let's confirm, does firm 1 have incentive to deviate? Does firm 1 have incentive to not invest, conditional on firm 2 investing? No, because then they'll go from 20 to -10. What about firm 2? Does firm 2 have incentive to not invest, conditional on firm 1 investing? No, because then they'll go from 10 to 0. So invest is a mutual best response. It's a Nash equilibrium. But there's something that might feel off about it in this case, which is, from the eyes of firm 1, yeah, 20 million is great. I'd love to earn 20 million. But what happens if firm 2 messes up somehow? If firm 2 chooses not to invest? Are you really willing to risk a $100 million loss on the manager of firm 2 who you might not even know, you might not even like? Is there another way to play this game that you're not putting a $100 million loss on the line? And the answer is to follow what's known as a max-min strategy. What this means is you want to take the worst case scenario and do the best you can in the worst case scenario. So let's consider firm 1's 2 strategies. We don't know what firm 2 is going to do, but what is the worst that firm 1 can do if they don't invest? The worst that firm 1 can do if they don't invest is lose 10 million. What if firm 1 invests? What is the worst firm 1 can do if they invest? Lose 100 million. So how do we do the best we can with the worst case scenario. How do we maximize our minimum here? We don't invest. Where either we earn 0 or we lose 10 million. Why might we choose to play a max-min strategy? Well, perhaps we're particularly risk averse, or perhaps we have not a certainty of what firm 2 is going to do, but we have a sense of their probabilities. In either case, Chapter 5 is a good review for this material. So suppose we're unsure of what firm 2 is going to do, but we have a sense that there is a 10% chance that they don't invest. What this implies is a 90% chance that they do. 90%. From here, we can calculate the expected value in both situations. And note, we only have to calculate expected value for firm 2 because as firm 1, we will make our decision with certainty. And then we just compare the expected values in the two states of the world. So if we think there's a 10% chance that firm 2 does not invest, and let me recreate our payoff table over here. We've got 0, 0. We've got minus 10, 10. We've got minus 100, 0. And we've got 20, 10. With the choices being no investment and investment. So let's go through that expected value calculation. If we think there's only a 10% chance that firm 2 does not invest, which would put them in this column right here, then what is our expected payoff from investing? Well, there's a 10% chance that we lose $100 million and a 90% chance that we gain 20 million, which is an expected value of 8 million. Similarly, if we think that 10% chance of firm 2 not investing exists, our expected payoff from not investing is a 10% chance of 0 and a 90% chance of losing 10 million with an expected loss of 9 million. In this case, firm 1 will invest. What if we have a different estimated probability? What if this time around we think the probability that firm 2 doesn't invest, the probability that firm 2 plays N is 30%? Here, our expected value from investing is a $16 million loss, and our expected value from not investing is a $7 million loss. So in this case, we choose to not invest. The canonical game theory game, you might have seen this before, is called the prisoner's dilemma. You and your buddy are out, you rob a bank, and the cops catch you. They put you in 2 different interrogation rooms. And this is what the police really do. They split people up when they're interrogating them. They put you in 2 different interrogation rooms, and they say, listen, we've got enough evidence to get your friend. We've got enough evidence to get your friend. They're not going to talk, but we've got enough evidence anyway. So what we're asking you to do is just confess to your crime. It'll help us seal the case. We'll give you a slap on the wrist. We'll write you a ticket for jaywalking or something, and we'll put them away for robbing the bank. In the other interrogation room, they're giving your buddy the same deal. We've got your friend, we're trying to charge your friend, we're trying to put them away for good. If you just confess, we'll give you a slap on the wrist and get you out of here on a jaywalking ticket. In actuality, the reason they're interrogating you is they don't have enough evidence to get either one of you on bank robbery charges. So if neither of you confesses, maybe, you'll get some sort of fine for disturbing the peace, but it won't be going away for 10 years because you robbed a bank. And if you both confess, maybe you guys can work out a plea bargain together where it's not as severe as if one does and the other doesn't, but you'll both go to prison for, say, 5 years for robbing this bank. So press pause on the video and on your own, take a minute to find the Nash equilibrium in this game. Now, ideally, we don't want to go to prison for 5 years or 10 years. The efficient outcome is one in which neither prisoner confesses. But suppose you both don't confess. Suppose neither of you snitches, and someone gives you the opportunity to change. So you're here, let's say you're prisoner A, and you don't confess. You're going to prison for 2 years. If they give you a phone call to your lawyer, you're given the opportunity to change and get some sort of slap on the wrist for your crime. You have incentive to deviate from this don't confess outcome. Same thing for your buddy. What we see is the Nash equilibrium is the one in which both of you confesses. Because given that your buddy is ratting you out, if you don't confess, you're going away for 10 years. Same thing for them. So we have, in the prisoner's dilemma, an inefficient Nash equilibrium. This is interesting because confession is not just our Nash equilibrium strategy, but confessing is a dominant strategy for both players, which necessarily results in a Nash equilibrium. We'll also note that this is the other equilibrium concept we talked about, the max-min strategy. So between being a max-min strategy, a dominant strategy, and a Nash equilibrium, there's a sense that confessing, ratting out your partner, is a very strong equilibrium. And a lot of people take this to mean that everyone is always going to turn on you. But maybe we'll see next lecture why that's not the case. We'll wrap up this lecture with 2 other types of games really quick. Matching pennies is one in which you can see there's no Nash equilibrium in pure strategies. And by pure strategies, what we mean is you're always playing the same strategy. If you're player A, in this case of matching pennies, you're either always playing heads or always playing tails. But note that sometimes you can mix it up, and a mixed strategy is just that, where you randomize your choice between heads and tails. A mixed strategy is one in which the player makes a random choice, and random in the sense of random number generator, random choice between 2 or perhaps more strategies based on a set probability. And there's a very strong theorem in economics that there's always a Nash equilibrium result in mixed strategies. We'll go over how to calculate this in class, but for now, convince yourself that calling heads half the time and calling tails half the time is a mutual best response for both players. Finally, we'll wrap up with a game called Battle of the Sexes. In this game, we've got Jim and Joan. Jim likes to go to wrestling matches. Joan likes to go to the opera. Hang on, this is just all wrong. Why are we going to talk about something in these archaic 1950s terms when we don't have to bring gender roles or sex into it? We can talk about it in the way we talked about it before with President Wu and Dean Garrett. It's not Battle of the Sexes, it's Battle of the Admins. So this is the same game we saw at the start of class. President Wu likes to hang out at Vixen's Den. Dean Garrett likes to hang out at the boathouse. They both like to hang out with one another. Where should they go after work? Well, knowing what we know now, we should be able to identify the 2 pure Nash equilibria strategy, either both going to the boathouse or both going to the den. Clearly, if you're at the same place as your friend, no one wants to go to a different place and be all alone. But the interesting thing here is that Dean Garrett likes the boathouse better, and President Wu likes Vixen's Den better. So there are also mixed strategy Nash equilibria, in which Dean Garrett chooses the boathouse with probability 2/3 and the den with 1/3, and President Wu chooses the boathouse with probability 1/3 and the den with probability 2/3. The problem with choosing these mixed strategies, and again, we're going to go over this more in detail in class, but unless they're either very risk-loving, they're going to reduce their playoff by playing a mixed strategy. Whereas if they play a pure strategy Nash equilibrium, at worst, one of them gets a payoff of 1. That's it for this time. Next time, we're going to go over some of these games in more detail with more examples, and we'll also draw on Chapter 12, which we didn't read for this class.